Today we're going to talk about rhenium. It's one of the hardest metals and obviously was a challenge to our technician Neil, who gave it the works. Hammer, acid, angle grinding. He eventually defeated it, and you'll see how. It also has very interesting history in terms of a volcano, and we found a really special sample of one of its minerals. Our friend Anthony Lippmann gave us some really nice pieces of rhenium, little pellets, which are surprisingly dense. Each of them weighs more than 20 grams. And he also gave us a sample of ammonium perrhenate, which is the compound that is used for purifying and recycling rhenium. Because rhenium is produced on very small scale in the world, but it's really important because its high melting point makes it a key component in the alloys that are used to make turbine blades in jet engines. You've probably recently been in a plane that had rhenium whizzing around inside the jet. It's not pure rhenium in the turbine blade, but an alloy, a mixture of rhenium with other metals. This was also present from Anthony. It's one that's been used already. They've chopped out a piece to stop me slipping it into my jet engine again. The value of these old turbine blades is that you can recycle the rhenium, and it's recycled by converting it into ammonium perrhenate. Rhenium is in the same periodic table group as manganese. It's at the bottom of the group. And potassium permanganate is purple and has lots of exciting reactions. Perrhenate is a bit more disappointing. It's white, it's very dense. Neil has never felt such a dense powder. We managed to dissolve it in water, and when we added potassium hydroxide, we got a precipitate, possibly potassium perrhenate or perhaps something else. But what was interesting and really excited Neil was that the precipitate formed rather slowly. Usually precipitation reactions are near instantaneous. With this, you could see it forming, and because the precipitate is so dense, it immediately settled to the bottom of the test tube, whereas usually you get a milky solution and you have to wait ages for any precipitate to settle. We tried lots of other reactions. Nothing worked well enough to interest you, or even to interest us. The reaction that did work quite well was putting the metal into concentrated nitric acid. The reaction's a bit slow to start. Needs to be warmed up with a Bunsen burner to get it going. But once it starts, you generate quite a lot of NO2, nitrogen dioxide. What was not clear is whether you made NO, which then reacted with oxygen in the air to make NO2, or whether the NO2 was coming out of the reaction at the start. But there was this impressive plume of brown gas coming out and lots of bubbling and a sort of grey solution left. But the nitric acid did clean the pellets, and that led us to do an experiment that was really quite interesting, and I'll tell you about that in a minute. So let me tell you a bit about the history of the discovery. It was almost discovered in 1908, 1909 by a Japanese chemist called Ogawa, but because there were no elements in the periodic table below manganese, he thought he had made element 43, the one we now call technetium. Unfortunately, in those days, before the First World War, he didn't have the X-ray techniques which could have confirmed the atomic number and told him that he'd made element 75. Then, after the First World War, the German chemist Ida Tucker revisited the absence of these elements and isolated an element from a mass of other minerals. And this is something which I think most modern chemists just couldn't do, taking kilos and kilos of rock and isolating milligrams of material from it. And she isolated enough to demonstrate with X-rays, which were taken by a colleague, that it was element 75. But her boss, Nodak, who later became her husband, was also a co-author of the paper.
What are you suggesting?
I think these stories are lost in the mist of time. Ida Tucker, I think, produced a gram of the element, or gram of its compound, and then after the Second World War, much larger quantities were isolated on an industrial scale, particularly from Kazakhstan, which in those days was part of the Soviet Union. I believe that at least some of the rhenium that was produced was used as nozzles for the rockets in the early Soviet space program. A really interesting discovery was made after the collapse of the Soviet Union on an island which is in the extreme east of the Russian landmass, one of the so-called Kuril Islands, which used to belong to Japan, which has active volcanoes on it. And one of these volcanoes, called Kudryavy, in Russian at least, has in the crater vents with steam coming out of them. The Russian geologist Genrich Steinberg climbed up to the top of the volcano, studied these vents with the gas coming out, and discovered that among other elements, it contained rhenium coming out in very small amounts. And then looking at the walls of the vent, or the beginning of the walls, because you can't probe very far down because they're so hot, they discovered a mineral which they called reniite, with a double I, which contained just rhenium and sulfur. Volcanoes always have a lot of sulfur, smell of bad eggs, and it's believed that these are formed by the reaction of hydrogen sulfide coming out of the vent reacting with oxides of rhenium. But what is really miraculous is that with all these elements coming out, somehow there is a selective reaction and it just reacts with rhenium and you get this pure mineral. This was a fantastic discovery. Nobody had ever discovered a rhenium mineral. It was published by Sternberg and his colleagues in the journal Nature, one of the most prestigious science journals there is. It was the cover article, and in these journals, when something's really exciting, they publish a little piece separately just explaining why it's so exciting, and in that little piece was a photograph of the mineral, the first picture that had ever been published. It's the first time that scientists or the public had ever seen it. Really excitingly, we have managed to find that sample, and Brady has videoed it. because our friend at the Natural History Museum, Mike Rumsey, has that sample in his collection.
So what I've got in the box is a super rare mineral. It's something called reniite. Not a lot of samples, not a lot of minerals actually contain rhenium as like a primary or really a lot of component to it. This is one of them. So rhenium is quite dominant in this material. We're lucky to have a few samples of it in the collection. It's the shiny silvery grey material that coats the rest of this sample. And it's from a volcanic fumarole. Pretty cool. So it's had a pretty amazing history. It was actually featured on Nature, which is quite cool. At this time, no one had really discovered a mineral where rhenium was so dominant that it was an essential part of the sample. So that was a big story.
Is that from the same volcano, or is that just happens to be?
No, it's from the same place. It's come to the museum through the author of that paper. And at that time, what's also quite interesting is it didn't have a name. So it was just a really rich mineral in rhenium, and it actually only got its name reniite about 10 years later.
What's more, he's even got the transparencies from their photo shoot showing all the different pictures of the same mineral. Brady likes to say it's a rock star. I would say it's just quite a famous sample.
What is it about this volcano that selects rhenium and you don't get rhenium around other similar vents? Is it just like, is it the temperature or the conditions, or like what's so magical here?
I'm not a geologist, but I think there are two different factors. First of all, you have to have a deposit of rhenium somewhere deep inside the volcano, and you don't find that everywhere. And then there is just a strange configuration of these vents which allows the high temperature and high pressure steam to carry up the vapor and get the reaction to occur. So I think it's a combination of having rhenium in the first place, having the hydrogen sulfide from the sulfur, and having the steam to carry everything along. In the paper in Nature, they stress how much more volatile, how much more easily vaporized the oxides of rhenium are than the metal itself. So after all this information about the oxides, of course, we wanted to see if we could make it ourselves. So we took one of the pellets that we'd been given just as it came out of the packet, and Neil heated it up in a Bunsen burner to really quite a high temperature. As he was heating it up, we saw a slight green colour in the flame, which looks as if it is the same as the green line which people report as the atomic spectrum of rhenium. But then, as he heated it up, it appeared to catch fire, but not very well. But when he took it out of the flame, you could see white smoke. And this smoke almost certainly was particles of oxide, which had condensed as they cooled in the air, which was really quite a nice demonstration of the fact that the oxide is really much more volatile than the metal. The metal didn't melt, but it appeared to produce this smoke for really quite a long time. So it wasn't just cooling down, there was some reaction. Once the pellet cooled down, there was a definite blackish colour, which is almost certainly the coating of oxide. But Neil made a really interesting observation that when he took one of the pellets that he'd cleaned in acid and heated it up, not to a very high temperature, that it formed really quite dark red coating, which corresponds to the colour of rhenium trioxide, ReO3. But if he heated it more, the red colour disappeared and the rhenium went black. So presumably the trioxide vaporized from the surface and a less volatile oxide was formed. Here you can see the two side by side, the black one at very high temperature and the red one at a rather cooler temperature with a cleaned pellet. Geologists got really excited about finding the rhenium in the vapor, and they thought perhaps they could use this vapor coming out of the vents to actually mine or collect rhenium. And they calculated that they might get up to 20 tons a year out of this one volcano, which in terms of world production is quite a sizable amount. So they built a small plant to actually test the idea, but after quite a short run, a week or two, they discovered that they'd only got 20 grams or so, and for some reason the rhenium was much harder to extract than they thought and wouldn't be commercial, at least with the process that they had. But it's really quite an exciting idea that you might be able to extract metals from the gases that are coming out of volcanoes. Obviously, you have to choose the right volcano to get the right minerals, and also you need to choose a volcano that won't suddenly erupt and send your factory down the slopes. At the beginning, I mentioned that Neil felt really challenged by rhenium. He tried filing it. But the file was damaged and the rhenium was completely untouched. He tried hitting it with a hammer. He made a mark on the metal plate underneath, but no mark on the rhenium. He then took a punch, which concentrates the blow, and hit that really hard.
Oops.
And he did make a small mark, but the punch flew off, ended up in Brady's camera bag. So in the end, he borrowed an angle grinder from our workshop, and that did eventually remove a bit of material from the surface, and he collected some of it on the sheet of filter paper. Now, we don't know what it is. It could be the rhenium, or it could be bits from the grinder itself. Neil nevertheless decided to burn it. He likes sprinkling powders into Bunsen burners. And so here is what we saw. It's up to you to decide, is this rhenium or is it something else? By the way, Genrich Sternberg died in 2020, and he asked that his ashes should be scattered on the volcano.
Maybe we should go and do a video there. Would you like to go there?
I think for somebody young like Brady, visiting it would be good, but you have to walk 4 days to get to the volcano, so I'm not sure that that's something for an old chap like me.
I'm not sure that's for me either. I'd like to go though.
Yeah. So we're here at the Royal Society of Chemistry for the celebration of the 99th birthday of rhenium.
It's a tradition in England. Who started what? And transparency.
Launched in 2018, we screened and we operate 2 primary.
And the audience here are about to see a preview of the video that you've just watched. I hope they'll like it. And while we were at the university filming with Brady, he was a bit bored by the colour of the rhenium compounds, so we thought he should see something a bit brighter. And our student Natalia produced a really nice rhenium phenanthroline complex, which is pretty bright yellow to look at. And when you put it under ultraviolet light, wow, you get really nice fluorescence. So it's rhenium in the middle with 3 carbonyl groups, CO groups bonded to the rhenium, a bromide, and the big organic phenanthaline group. So at the end, we all went to Neil's office, which has no windows, so we could really see the fluorescence brightly. And Brady changed his mind. He was really wowed by rhenium.